Welcome to the AI Coach by Anil Nathu. Today we're embarking on a deep dive into one of the most rapidly evolving and frankly often confused areas of artificial intelligence, the distinction between AI agents and agentic AI. Our mission, as always, is to take complex source material and distill it into those essential, crystal-clear insights that truly make you well-informed. We're drawing today from a really insightful review titled AI Agents versus Agentic AI. Conceptual Taxonomy, Applications and Challenges, authored by Ranjan Sepkoda, Konstantinos Sikpeyour-Maliotis, and Manoj Karki, researchers from Cornell University and the University of the Peloponnese. This paper offers what I consider a definitive roadmap for understanding these systems. So the big question we're tackling today is, what truly sets an AI agent apart from agentic AI, and why does this distinction matter for you, the curious learner, and for the future of technology?
That's a crucial question, and to really appreciate where we are today, it's essential to understand the historical context of AI. Before November 2022, what we often call the pre-ChatGPT era, the development of autonomous intelligence was rooted in foundational paradigms like multi-agent systems, or MAS, and expert systems. These early approaches focused on concepts of distributed intelligence and problem solving. Think about systems like MYCIN, a pioneering expert system from the 1970s designed for medical diagnosis. It used extensive knowledge bases and inference engines to mimic human doctors' decision-making processes, but it was essentially a complex rule-based engine.
Right, like a big if-then machine.
Exactly. Or consider the Stanford cart, an early autonomous robotic system developed in the late 70s. It could navigate a room using cameras, but its movements were based on hard-coded rules and a simple sense-act cycle. Even early non-player characters in video games or agents used in air traffic control simulations with belief, desire, intention architectures followed predefined decision trees. The key takeaway from this era is that these systems were predominantly rule-based, quite limited in their autonomy, and fundamentally lacked the capacity for self-learning or dynamic adaptation to new environments. They were intelligent, but, in a very constrained way.
Very constrained. Okay.
Then came November 2022. The public release of ChatGPT wasn't just another tech launch. It was a pivotal inflection point that catalyzed a global surge in AI adoption, investment, and research.
A real game changer.
Absolutely. Suddenly, terms like AI agents and agentic AI exploded into public and academic discourse. If you look at global search trends, you'd see a dramatic upward curve for both terms right after ChatGPT's emergence, signaling a widespread recognition that something new was doubling up.
Everyone started talking about agents.
Yes, and this has led to a fascinating evolution trajectory. Initially, we saw the popularization of what we now call generative agents. Think GitHub Copilot for writing code, Jasper for generating marketing copy, or Midjourney for creating stunning images from text prompts. These were powerful LLM-based systems focused on producing novel outputs, but they were largely passive, waiting for a prompt.
Just generating stuff.
Right. The next phase brought us AI agents. These systems took those powerful LLMs and enhanced them with external tool use, function calling, and the ability to perform sequential reasoning, enabling multi-step workflows. This is where systems like AutoGPT and Baby ATI emerged, demonstrating a new level of proactivity.
Okay, so they could do things.
Exactly. And finally, by late 2023, the field progressed into agentic AI complex multi-agent systems where specialized AI entities collaboratively decompose large goals and coordinate their efforts, much like Crew AI. It's a clear, accelerating progression in capabilities.
Wow, that's quite the evolution in just a short time.
It really is. And this brings us to why this conceptual framework, or taxonomy as the paper calls it, is so significant. It's not just academic jargon. It's a critical lens for designing and deploying effective AI systems. Understanding these distinctions enables precise system design, ensuring you pick the right tool for the job.
Makes sense.
For instance, you deploy AI agents for modular, tool-assisted tasks and reserve agentic AI for more orchestrated, complex, multi-agent operations. It also allows for appropriate benchmarking and evaluation because performance metrics, safety protocols, and resource requirements differ vastly between a single task-specific agent and a distributed, collaborative system.
So you know what you're measuring.
Precisely. And crucially, this clarity reduces development inefficiencies. Without it, as the paper warns, practitioners risk two major pitfalls: under-engineering complex scenarios that truly demand multi-agent coordination,
Using the wrong tool for a big job.
or over-engineering simple applications that a single AI agent could easily solve.
Building something way too complex for a simple task.
Exactly. This deep dive will give you the foundational understanding to avoid those costly missteps. It's about not using a sledgehammer for a nail, nor a nail for a concrete wall. That's the practical power of this taxonomy.
That sets the stage beautifully. So let's unpack this foundational concept. What exactly is an AI agent? The paper defines AI agents as autonomous software entities engineered for goal-directed task execution within bounded digital environments. They essentially act as intelligent surrogates for human users or subsystems. Now, what truly distinguishes an AI agent from conventional automation, those deterministic scripts that simply follow a predefined, rigid workflow.
Right, the old way.
AI agents are fundamentally different. Unlike those, they demonstrate what the paper calls reactive intelligence and limited adaptability. This means they can interpret dynamic inputs, things that change in real time, and then reconfigure their outputs accordingly. They're not just following a rigid set of instructions, they're responding to a shifting landscape, showing a basic form of responsiveness.
Exactly. And the paper identifies 3 foundational characteristics that are consistently found across virtually all real-world deployments of AI agents.
Okay, so what do I...
First up, we have autonomy. This refers to the agent's ability to function with minimal or no human intervention after deployment. Think about that. Once an AI agent is initialized and given its core mission, it's capable of perceiving environmental inputs, reasoning over contextual data, and executing actions all on its own.
So you set it up and let it run.
Pretty much. This autonomy is what allows for large-scale, unattended operations. A great practical example is a customer support bot that can handle routine queries independently, routing complex issues to human agents only when absolutely necessary. Or a scheduling assistant that manages your calendar for an entire week, proactively finding optimal meeting times and resolving conflicts without you having to constantly oversee it after the initial setup. They are designed to operate independently once given their mission.
Got it. Autonomy. What's second?
Second, there's task specificity. AI agents are, by design, purpose-built for narrow, well-defined tasks. They are optimized for repeatable operations within a fixed domain. This specialization is a major strength because it means they're not trying to do everything. Instead, they become exceptionally good at one or a few closely related things.
Like a specialist versus a generalist.
Precisely. Imagine an email filtering agent that precisely classifies urgent emails, or a database querying agent that pulls very specific information based on a natural language request, or even a calendar coordination agent focused solely on managing appointments and sending invites. This laser focus leads to immense efficiency, interpretability, and high precision in their automated tasks. They excel because they are highly specialized.
Okay, autonomy and task specificity. And the third?
And finally, we have reactivity and adaptation. This describes the agent's capacity to respond to changes in its environment. This could be anything from a new user command, a shift in software states, or a response from an external API. The paper highlights that some of these agents even include rudimentary learning through feedback loops, heuristics, or updated context buffers. This allows them to refine their behavior over time.
Because I can learn a little.
A little, yes, rudimentary learning. Consider a personalized recommendations agent that learns your preferences as you interact with it, subtly shifting its suggestions from crime thrillers to historical dramas as your tastes evolve. Or a conversation flow management agent that improves its responses based on past interactions, making the dialogue smoother and more relevant each time. These feedback mechanisms, even if basic, are crucial for their dynamic nature and ability to respond intelligently to a changing world.
Okay, that makes sense. Autonomy, task specificity, and reactivity adaptation. This is where it gets really interesting. The crucial role of foundational models empowering these agents. It's not just about the agent's design, but the sophisticated intelligence that lies beneath.
Absolutely, the models are key.
Large language models, or LLMs, like GPT-4, Palam, Claude, and Llama, are truly the core reasoning components. These models are trained on massive data sets of text and provide incredible capabilities such as natural language understanding, question answering, summarization, dialogue coherence, and even symbolic reasoning. But here's the key part for agents. They are purposefully repurposed. In an agent's architecture, LLMs serve as the primary decision-making engine. They are responsible for parsing your queries, planning multi-step solutions to complex problems, and generating natural language responses.
The brain of the operation.
Exactly. Think of an AI customer support agent powered by GPT-4. It can interpret nuanced customer complaints, then query various back-end systems through tool integration to find relevant information, and finally construct a contextually appropriate and empathetic response. This capability for understanding and structured reasoning is a core offering and a key area of innovation at AI Coach by Anil Nathu, helping businesses leverage these powerful capabilities.
It's a huge leap from rule-based bots.
Totally. But it's not just language. We also have large image models, or LLMs, like CLIP and Bill2. These models extend agents into the visual domain, enabling tasks like image classification, object detection, and vision language grounding. This capability is vital for agents that operate in the physical world or deal with visual data.
Seeing the world, basically.
Right. Let's elaborate on a fascinating real-world application, an autonomous drone agent tasked with inspecting orchards. This drone uses a limb to identify diseased fruits or damaged branches by interpreting live aerial imagery. Once detected, it doesn't wait for human input. It automatically triggers predefined intervention protocols, such as notifying horticultural staff or precisely marking locations for targeted treatment, all without requiring human intervention. This perfectly demonstrates the AI agent's autonomy and reactivity in a very tangible way.
That's incredible. So the drone sees a problem and acts on it.
Exactly. Research in this area, work by Chitra et al. And Krav et al., consistently highlights how AI algorithms combining computer vision, mapping, sensor fusion, and LLM-driven action planning are advancing drone-based agents. It all underscores the critical importance of AI-driven autonomy, perception, and decision-making for these future systems.
Yeah, the potential there is enormous. But it's important to understand that generative AI, while incredibly impressive and revolutionary in its own right, functions as a precursor to these more sophisticated AI agents. Generative AI systems primarily synthesize novel content, text, images, audio, or code based on input prompts. They are, at their core, output generators.
They make stuff.
They make stuff. There are key characteristics that define them. First, their reactivity. They are exclusively input-driven, meaning their operations are triggered solely by user prompts. Crucially, they lack internal states, persistent memory, or goal-following mechanisms. They don't autonomously pursue goals. They simply wait for instructions and then generate a response.
Passive.
Very passive. Second, they often boast multimodal capability. Modern generative systems like GPT-4 and Blade-2 can produce diverse outputs, from coherent narratives and executable code to realistic images and even speech, bridging different forms of media. However, a crucial defining characteristic is their prompt dependency and statelessness. Generative systems do not retain context across interactions unless explicitly provided.
Goldfish memory.
Kind of, yeah. This means they're essentially stateless. They don't remember what happened in previous interactions unless you explicitly remind them in each new prompt. They also lack intrinsic feedback loops or multi-step planning, which are fundamental for autonomous decision-making and iterative goal refinement.
Okay, so that's a big limitation.
It is. This brings us to the critical gap. While generative AI is fantastic for content creation, it cannot act upon the environment or manipulate digital tools independently. It can't, for example, search the internet for real-time data, interact with your email client, or query an API unless a human provides a specific wrapper or scaffolding layer.
It needs help to interact.
Precisely. This is exactly why they aren't classified as true AI agents, which inherently integrate perception, decision-making, and external tool use within closed feedback loops. They're powerful for creation, but they're passive responders, not active doers.
That critical gap in generative AI naturally leads us to the next evolutionary step: the development and widespread adoption of AI agents, driven largely by the repurposing of large language models.
Exactly, filling that gap.
LLMs, like GPT-4, PaLM, Claude, and Llama, are no longer just about generating responses. They're being used as cognitive substrates within these dynamic agentic systems. This means they interpret complex user goals, generate sophisticated action plans, strategically select the right tools for a given task, and then manage intricate multi-turn workflows.
They're thinking and doing.
Right. Think of systems like AutoGPT and Baby AGI. The paper highlights how they use a powerful LLM like GPT-4 as both a planner and executor. The LLM analyzes high-level objectives, breaks them down into actionable subtasks, invokes external APIs as needed, and continuously monitors its progress, making decisions about the next steps. It's essentially a loop of prompt processing, state updating, and feedback-based correction, truly beginning to emulate autonomous decision-making.
That loop is really the core of it.
Now, to overcome the inherent limitations of generative-only systems, like their tendency to hallucinate, their static knowledge cutoff, or their restricted interaction scope, we see the rise of tool-augmented AI agents. These systems are specifically designed to integrate external tools, APIs, and computation platforms into the agent's reasoning pipeline. This allows for real-time information access, code execution, and interaction with dynamic data environments, moving beyond static knowledge.
Giving the LLM superpowers, essentially.
Kind of. The mechanism here involves two key steps: tool invocation and result integration. During tool invocation, if an agent identifies a need that its internal knowledge can't address, say, checking a live stock price or retrieving the current weather, it generates a structured function call or API request.
Asking for help from the outside world.
Exactly. These calls are typically formatted in clear, machine-readable formats like JSON, SQL, or Python, and then routed through an orchestration layer that executes the task. Once the response comes back from the tool, that's result integration. The output is parsed and then reincorporated back into the LLM's context window. This empowers the agent to synthesize new reasoning paths, update its task status, and decide on the next optimal step.
So it uses the tool's output to figure out what to do next.
Precisely. The React framework, which combines reasoning, chain of thought prompting, and action tool use, is a prime example of this, allowing LLMs to alternate between internal cognition and external environment interaction.
Think, act, observe, think again.
That's the cycle. Let's consider some compelling examples. An AutoGPT agent might plan and execute a product market analysis. This isn't just generating text. It involves a sequence of actions: sequentially querying the web for market trends, compiling competitor data by interacting with external sources, summarizing the insights from that data, and finally generating a comprehensive report.
Wow, that's complex.
It is. For coding, tools like GPT Engineer combine LLM-driven design with local code execution environments to iteratively develop software. In research, PaperQA uses LLMs to query vectorized academic databases, ensuring answers are grounded in retrieved scientific literature, which effectively prevents those pesky hallucinations.
Grounding is so important.
Absolutely. These agents are dynamic cognitive entities, capable of perceiving, planning, acting, and adapting, a far cry from simple generative models.
So if AI agents are already so capable handling tasks and even using external tools, what's the next frontier?
Good question.
The answer is agentic AI, which represents a major conceptual leap forward. While single AI agents are excellent for narrow, well-defined tasks, they face inherent limitations. The paper highlights that they struggle with scalability in complex, multi-step, or cooperative scenarios. They also often lack sufficient context retention and adaptability across highly dynamic environments. This is precisely what agentic AI aims to solve.
Okay, so agentic AI is about handling bigger, more complex stuff.
And handling it collaboratively. The conceptual leap here is truly significant. It's a shift from isolated tasks to coordinated systems, where an individual AI agent uses an LLM and external tools to execute narrowly scoped operations. Agentic AI systems are defined as intelligent architectures, where multiple specialized agents collaborate to achieve complex, high-level objectives.
Multiple agents working together. A team.
Exactly, a team. The paper emphasizes that these systems are composed of modular agents, each contributing a distinct subcomponent to a broader goal, and then coordinated by either a centralized orchestrator or a decentralized protocol. This is a fundamental departure from the single atomic reactive behaviors of individual agents.
So it's not just one agent anymore.
Nope. Several key enablers make this new paradigm possible. First, goal decomposition. A user's complex objective is automatically parsed and divided into smaller, manageable tasks by planning agents. These subtasks are then intelligently distributed across the network of specialized agents.
Breaking down the big problem.
Exactly. Second, multi-step reasoning and planning mechanisms facilitate the dynamic sequencing of these subtasks, allowing the system to adapt in real time to environmental shifts or even partial task failures, ensuring robust execution even under uncertainty.
Adapting on the fly.
Third, interagent communication is vital. This is mediated through distributed channels like asynchronous messaging queues, shared memory buffers, or intermediate output exchanges, enabling seamless coordination without needing constant central oversight.
The agents talk to each other.
They have to. And finally, reflective reasoning and memory systems allow these agents to store context across multiple interactions, evaluate past decisions, and iteratively refine their strategies. All of these capabilities together enable agentic AI systems to exhibit a flexible, adaptive, and collaborative intelligence that far surpasses the operational limits of individual agents.
That sounds incredibly powerful.
It really is. To really grasp this, let's use a very relatable analogy: the smart home. Imagine, for a moment, your basic smart thermostat. It receives a temperature setting, and it autonomously controls your heating or cooling. It might even learn your schedule to save energy. This is a classic example of an AI agent.
Got it. One device, one job.
Right. It's single task focused, operates in relative isolation, and while autonomous within its defined scope, it has no broader coordination with other systems in your home. It's a deterministic component with limited scope. Now, compare that to a comprehensive smart home ecosystem. This is Agentic AI in action. Here, you have multiple specialized agents interacting synergistically.
Ah.
A weather agent signals an upcoming heat wave, which then prompts an energy management agent to pre-cool your home using solar power before peak electricity pricing hours. At the same time, your smart home system might integrate with your daily schedule, activated by a scheduling agent, to delay high-energy tasks like laundry until you're out, or even activate your security systems when you leave.
Whoa, that's true coordination.
Exactly. This demonstrates distributed intelligence, characterized by goal decomposition, inter-agent communication, and contextual adaptation. It's not just a collection of smart devices, it's a unified adaptive system with emergent behaviors arising from intelligent collaboration. It's a powerful vision, one that AI coach by Anil Nathu truly believes in for future innovation.
That smart home analogy really paints a vivid picture. So it's not just more smart devices, but a symphony of them working together. It's a powerful shift. Let's look at the key differentiators more formally. What becomes clear is how agentic AI truly built upon generative AI and AI agents, introducing increasing layers of sophistication.
Yeah, the tables in the paper lay this out really well.
For example, if we consider autonomy level, generative AI is merely prompt-triggered. It sits there waiting for your input.
Passive.
If AI agents demonstrate high autonomy within specific tasks, they can act independently within an assigned scope once given a goal. But agentic AI steps up to higher autonomy with the ability to manage multi-step complex tasks. It manages entire processes, not just individual actions.
Much more proactive and comprehensive.
In terms of task complexity, AI agents typically handle single specific tasks. They're specialists, great at one thing. Agentic AI, however, handles complex, multi-step tasks requiring coordination. It's about solving bigger, interconnected problems that require breaking down a large objective into smaller parts.
Scale and complexity go way up.
And a crucial difference is collaboration. AI agents largely operate independently. They don't inherently talk to other AI systems to achieve a shared goal. Agentic AI, by its very definition, involves multi-agent collaboration and information sharing. They work as a true team.
Collaboration is the defining feature, really.
Looking at architectural composition, generative AI is a single model. AI agents are an LLM plus external tools, meaning an LLM augmented with capabilities to interact with the world. But agentic AI is a full multi-agent system that includes essential orchestration and often involves multiple LLMs, each potentially specialized for different roles.
A much more complex structure.
Definitely. Finally, considering the operational mechanism, generative AI is simply reactivity to a prompt. AI agents use tool calling for task execution to interact with the world and perform actions. But agentic AI relies heavily on interagent communication and collaboration. The flow of information and decision-making across the system is fundamentally different.
How they work is different.
This systematic comparison highlights that the evolution is not just incremental, but represents distinct paradigms with increasing levels of operational independence and sophisticated coordination.
Moving from the conceptual to the concrete, let's dive deeper into the architectural evolution, from AI agents to agentic AI systems. The transition from a single AI agent to an agentic AI system involves significant enhancements to the underlying architecture, building on the foundational components.
Okay, how do they differ under the hood?
Traditional AI agents, at their core, are composed of four primary subsystems, forming a closed-loop operational cycle often described as understand, think, act. First, there's the perception module. This is the agent's eyes and ears. It's responsible for ingesting all sorts of input signals, whether they're natural language prompts from a user, data from APIs, file uploads, or even real-time sensor streams. It processes this raw data into a format that the agent's reasoning module can understand. For example, in agents built with modern frameworks, the perception layer handles complex tasks like contextual wrapping and retrieval augmentation, which involves finding and embedding relevant past information to ground the agent's response.
Taking in the information.
Right. Next, we have the Knowledge Representation and Reasoning (KR) module. This is the brain of the agent. It applies various forms of logic, whether it's simple rule-based decision-making or more complex planning to the input data. In more advanced agents, reasoning is enhanced through function calling and prompt chaining, allowing the agent to simulate a step-by-step thought process, often by invoking intermediate tools to aid its logic.
The thinking part.
Then comes the Action Selection and Execution module. This module translates the decisions made by the KRR into external actions. These actions could be anything from sending messages, updating databases, querying external APIs, or producing structured outputs. This module is how the agent actually does things in the world.
Making things happen.
And finally, there's basic learning and adaptation. Traditional AI agents have somewhat limited learning mechanisms. This might involve heuristic parameter adjustment, where the agent tweaks its internal settings based on performance, or history-informed context retention, using simple memory buffers to recall prior user inputs or improve tool selection over time. While this provides some context awareness, it's not deep, continuous learning in the human sense.
So a basic agent architecture, how does agentic AI build on that?
Agentic AI systems, however, inherit this modularity but take it much further. They introduce critical architectural enhancements to support distributed intelligence, interagent communication, and recursive planning. First, we see an ensemble of specialized agents. Instead of one monolithic unit, agentic AI systems are comprised of multiple agents, each with a highly specialized function.
Like a team of specialists.
Exactly. Think of a team. You might have a summarizer agent, a retriever agent, or a planner agent all working together. These agents communicate and interact through dedicated channels like message queues or shared memory spaces. A great real-world example is MetaGPT, which models its agents after corporate departments like a CEO, CTO, or engineer, where each role is modular, reusable, and clearly defined, each contributing to a larger project.
Interesting. Like an org chart for AI.
Kind of, yeah. Second, agentic AI features advanced reasoning and planning. These systems embed recursive reasoning capabilities using sophisticated frameworks such as chain of thought prompting and tree of thoughts. These mechanisms allow the agent to break down a complex task into multiple, smaller reasoning stages, evaluate intermediate results, and dynamically replan actions if something unexpected happens. This is crucial for adapting to uncertainty or recovering from partial failures in real time.
Deeper thinking and planning.
Third, they employ persistent memory architectures. Unlike basic agents, agentic AI systems integrate robust memory subsystems to retain knowledge across multiple task cycles or agent sessions. This includes episodic memory, which stores task-specific history, semantic memory for long-term facts and structured data, and vector-based memory, often used for retrieval-augmented generation. For instance, in multi-agent systems, agents maintain scratch pads for intermediate computations, enabling seamless stepwise task progression even across complex, long-running workflows.
Better memory, basically. Shared memory, even.
Yes, often shared memory is key. And a key innovation, the fourth enhancement, is the orchestration layers, often managed by meta-agents. These meta-agents coordinate the entire lifecycle of the subordinate agents. They manage dependencies, assign roles, and actively resolve conflicts that arise. Orchestrators might function as task managers, evaluators, or even moderators.
As a manager of the agent team.
Exactly. In the ChatDev framework, for instance, a virtual CEO meta-agent distributes subtasks to departmental agents and integrates their outputs into a unified strategic response. This highlights the layered modularity in agentic AI that AI coach by Anil Nathu emphasizes as critical for future system design. These enhancements signify a profound shift to more reflective, decentralized, and truly goal-driven system architectures. It's no longer just about individual intelligence, but about coordinated, collective intelligence.
Okay, that architectural breakdown really clarifies the step up. Now, this is where the rubber truly meets the road. What can these different types of AI actually do in the real world? It's fascinating to see how they're already transforming industries.
Absolutely. Let's deep dive into AI agent applications first. These are typically single-agent systems focused on specific tasks.
The specialists.
Right. One prominent application is customer support automation and internal enterprise search. AI agents are widely adopted here, using retrieval-augmented generation, or RG, and APIs to answer queries and triage tickets in customer support, or retrieve semantically relevant documents for internal enterprise search. Think about how Salesforce Einstein or Notion AI streamline workflows. For instance, imagine a multinational e-commerce company deploying an AI agent for customer support. This agent integrates with the company's CRM and fulfillment APIs to resolve queries like, "Where is my order?" or "How can I return this item?" It retrieves contextual data from shipping databases and policy repositories within milliseconds, then generates a personalized response using RG.
Instant answers grounded in real data.
Exactly. This drastically reduces ticket volume and support overhead, freeing up human agents for more complex issues.
That makes sense. What else?
Another significant use is email filtering and prioritization. In modern workplaces, we're inundated with emails, and AI agents embedded in tools like Microsoft Outlook or Superhuman act as intelligent intermediaries. They classify, cluster, and triage incoming messages by evaluating their content and semantic meaning to detect urgency, extract actionable items, and even suggest smart replies.
Sorting the inbox chaos.
Precisely. The agent can autonomously categorize emails into urgent, follow-up, or low priority, offering concise summaries and reply drafts. Through continual feedback, it adapts to your preferences, refining its classification and prioritization. This automation significantly offloads decision fatigue, allowing you to focus on high-value tasks.
I could use one of those.
Couldn't we all? Moving to personalized content recommendation and basic data reporting, AI agents support adaptive personalization by analyzing your behavioral patterns for news, products, or media. Platforms like Amazon, YouTube, and Spotify use these agents to infer your preferences via collaborative filtering and intent detection, dynamically generating suggestions that evolve over time.
Like suggesting the next show to watch.
Exactly. For example, an Amazon agent monitoring your browsing and purchases might recommend soil sensors after you buy gardening tools, enhancing your engagement. In a corporate setting, an AI agent in Power BI Copilot allows non-technical staff to ask natural language questions like, compare Q3 and Q4 sales in the Northeast. The agent translates this into appropriate queries, extracts patterns, and outputs a concise visual summary or narrative report, effectively democratizing business intelligence.
Making data accessible to everyone.
Right. Finally, consider autonomous scheduling assistance. AI agents integrated with calendar systems autonomously manage meeting coordination, rescheduling, and conflict resolution. Tools like X.AI and Clockwise interpret vague commands, access calendar APIs, and identify optimal time slots based on learned user preferences.
The end of scheduling back and forth.
That's the dream. Imagine an executive assistant AI agent integrated with Google Calendar and Slack. You simply tell it, find a 45-minute window for a follow-up with the product team next week. The agent parses the request, checks availability for all participants, accounts for time zone differences, avoids conflicts, proposes alternatives, and even learns your preferences, like avoiding early Friday meetings. This proactive management significantly reduces coordination overhead and increases scheduling efficiency.
Those are powerful examples of what single AI agents can do. Now let's explore the more advanced agentic AI applications where collaboration takes center stage. This is a powerful vision that truly unlocks new levels of automation and problem solving.
Absolutely. Agentic AI applications leverage multiple agents to achieve complex, collaborative goals that a single agent simply couldn't handle.
The team players.
Exactly. One incredibly promising area is multi-agent research assistance. Agentic AI systems are increasingly used in academic and industrial research pipelines to automate multi-stage knowledge work. Platforms like Autogen and Crew AI assign specialized roles to multiple agents. You might have retrievers, summarizers, synthesizers, and citation formatters all working under a central orchestrator.
A research team made of AI.
Pretty much. Imagine a university research group preparing a complex grant proposal. You could have agents that retrieve prior funded proposals to extract structural patterns, another that scans recent literature for related work, a third that aligns proposal objectives with the funding agency's solicitation language, and a fourth that structures the final document, ensuring all guidelines are met. The orchestrator coordinates them, resolves dependencies, and ensures consistency. Persistent memory modules store evolving drafts and feedback, enabling iterative improvement.
That must save a huge amount of time.
It does. This system significantly accelerates drafting time, improves narrative cohesion, and ensures regulatory alignment, which is critical for success.
Amazing. What about physical applications?
Another groundbreaking application is intelligent robotics coordination. In advanced manufacturing, logistics, and agriculture, agentic AI underpins collaborative behavior in multi-robot systems. Each robot operates as a specialized agent, a picker, a transporter, or a mapper, while an orchestrator supervises and adapts workflows, using shared spatial memory and real-time sensor fusion.
Like the orchard example, but scaled up.
Exactly. Consider commercial apple orchards utilizing a coordinated multi-robot system. Drones, using vision models, first map the orchard and identify ripe clusters. This spatial data is shared via a central memory layer accessible to all robots. Picker robots are then assigned to high-density zones, guided by path planning agents. Transport agents dynamically shuttle harvested crates. All agents communicate asynchronously, and the orchestrator continuously adjusts task priorities based on real-time factors like weather changes or mechanical faults.
So they react to problems.
Yes. If a picker robot fails, nearby units can autonomously reallocate its workload. This adaptive coordination significantly reduces labor costs and increases harvest efficiency, far surpassing rigid, pre-programmed robotic systems.
Incredible adaptability.
Then there's collaborative medical decision support. In high-stakes clinical environments, Agentic AI enables distributed medical reasoning. Specialized agents handle tasks like diagnostics, vital monitoring, and treatment planning.
AI helping doctors.
Precisely. Imagine a hospital ICU. A diagnostic agent continuously analyzes patient vitals for early sepsis risk. A history retrieval agent summarizes electronic health records, pulling out key events. And a treatment planning agent cross-references symptoms with the latest clinical guidelines and drug interactions. The orchestrator integrates these insights, ensures consistency across findings, and flags any conflicts for human-physician review. Feedback from physicians is stored in a persistent memory module, allowing agents to refine their reasoning over time.
That could genuinely save lives.
That's the hope. This system profoundly enhances clinical workflow by reducing cognitive load on medical staff, shortening decision times, and minimizing oversight risks, ultimately improving patient outcomes.
Wow. Any other examples?
Finally, Agentic AI is transforming multi-agent game AI and adaptive workflow automation in enterprise settings. In complex simulation environments or within a modern enterprise IT landscape, Agentic AI facilitates decentralized task execution and emergent coordination. Take cybersecurity incident response. When a threat is detected, specialized agents activate in parallel. One performs real-time threat classification. Another queries relevant log data across various systems. A third interprets compliance frameworks to understand regulatory implications. And a fourth simulates potential mitigation strategies to predict their impact.
A rapid response team.
Exactly. They coordinate under an orchestrator that evaluates their collective outputs and issues recommended actions to human analysts. The system learns from prior incidents, enabling faster and more accurate responses to emerging threats, reducing the window of vulnerability.
Okay, the potential is clearly immense, transforming everything from orchards to hospital ICUs. But there have to be challenges, right?
Yeah.
Significant hurdles to overcome with both AI agents and agentic AI.
Yeah.
What are the key limitations we need to be aware of as these systems become more prevalent?
Absolutely. The challenges are formidable. Let's first unpack the challenges specific to single AI agents.
All right, what holds them back?
One of the most foundational is the lack of causal understanding. Current LLMs, which power most AI agents, are excellent at identifying statistical correlations, but they fundamentally lack the capacity for causal modeling, distinguishing between mere association and cause-effect relationships.
They see patterns but don't know why.
Exactly. For example, an agent might know that hospital visits often coincide with illness, but it cannot truly infer whether the illness causes the visit or vice versa. Nor can it reliably simulate hypothetical changes like, what if we change this treatment?
Yeah.
This leads to brittleness in novel or high-stakes scenarios. A navigation agent that performs perfectly in sunny city driving might misbehave in snow or construction zones if it lacks an internal causal model of road traction and its implications.
They can break easily in new situations.
Right. Then there are the inherited limitations from LLMs themselves. We've touched on some, but they're critical. Hallucinations. These are those plausible but factually incorrect outputs that can lead to severe misjudgments and erode user trust, especially in critical domains like legal or scientific research.
Making stuff up confidently.
Prompt sensitivity brittleness. Even minor phrasing changes in a prompt can lead to entirely divergent behaviors, demanding meticulous and time-consuming manual prompt engineering to maintain consistency. Shallow reasoning. Despite techniques like chain of thought, agents remain shallow in semantic comprehension. They might follow a logical-seeming path, but still fail at multi-step inference, or make logically inconsistent conclusions.
Not really understanding deeply.
Computational cost and latency. Each decision cycle, especially involving planning or tool calling, can require multiple LM invocations, increasing runtime latency and resource consumption. This makes them expensive and slow for real-time critical applications.
Slow and expensive.
Static knowledge cutoff and biases. Unless explicitly augmented, LLMs have a knowledge cutoff, meaning they can't dynamically integrate new information. And they reproduce the biases of their training datasets, leading to culturally insensitive or skewed responses.
Outdated and potentially biased. That's a lot.
It is. A third key limitation is limited long-horizon planning and recovery. Agents struggle with robust long-horizon planning in complex multi-stage tasks due to their fundamental stateless prompt response paradigms. They essentially start fresh with each prompt unless memory is explicitly engineered.
Can't plan far ahead easily.
Right. They often falter in tasks requiring extended temporal consistency, like clinical triage or financial management, exhibiting repetitive behaviors or failing when subtasks yield ambiguous results. The absence of systematic recovery mechanisms makes them brittle and prone to getting stuck.
So single agents have their challenges. But this leads to even more complex challenges when we introduce multiple agents, where interactions can create unforeseen problems. It's a fascinating new frontier, and it's important for us at AI Coach by Anil Nathu to highlight these real-world complexities so you're prepared.
You're absolutely right. The challenges with agentic AI are often amplified and novel, precisely because of the inherent complexity of multi-agent interactions.
Okay, what new problems arise with agent teams?
First, we face amplified causality challenges. In agentic AI, where one agent's action influences others, the causality deficits observed in single agents are magnified. This can lead to inter-agent distributional shift, where one agent's behavior unexpectedly alters the context for others, causing coordination breakdowns. Even worse, there are error cascades. A faulty or hallucinated output from one agent can propagate through the system, compounding inaccuracies.
One bad apple spoils the bunch.
Exactly. For example, if a verification agent mistakenly validates false information, downstream agents will unknowingly build upon that misinformation, compromising the entire system's integrity.
Yikes.
Second, communication and coordination bottlenecks are significant. Achieving truly efficient collaboration across multiple autonomous agents is incredibly difficult. Issues include goal alignment and shared context, where agents might lack a unified semantic understanding of the overarching objectives. Protocol limitations mean most systems rely on natural language exchanges, which are prone to ambiguity and contextual drift, leading to fragmented strategies. And resource contention arises when agents simultaneously access shared computational or API resources, causing race conditions or system failures.
Getting them to understand each other and share resources is hard.
Very hard. Third is emergent behavior and predictability. While emergent behavior can be adaptive and exciting, it also introduces significant unpredictability. This includes unintended outcomes, behaviors not explicitly programmed that might diverge from objectives or even cause harm. System instability can manifest as infinite planning loops, deadlocks, and contradictory behaviors as interactions grow.
They might do things you never expected.
And not always good things. The stochasticity and opacity of large language model-based agents make their internal logic extremely hard to interpret or verify, making predictability a central unsolved challenge.
Hard to predict, hard to understand.
Fourth, scalability and debugging complexity become immense. The black box chains of reasoning across multiple agents make tracing failures extremely difficult, requiring unwinding nested sequences of agent interactions to find the root cause. Finding the bug is a nightmare, pretty much. Furthermore, there's non-compositionality. Simply adding more agents doesn't guarantee improved performance. It can actually increase cognitive load, noise, and coordination overhead, making the system less efficient.
More agents isn't always better.
Not necessarily. And finally, a broad category of challenges relate to trust, explainability, and verification. With multiple asynchronous agents, there's compounded opacity, where tracing the causal chain of a final decision is very difficult. The lack of shared transparent logs and the absence of formal verification tools for multi-agent LLM systems are significant barriers to adoption in safety-critical domains where guarantees are paramount.
Huge trust issues.
These systems are incredibly powerful, but these challenges highlight the need for extensive research and development before widespread, unmonitored deployment.
These challenges are certainly formidable, but they also highlight where the cutting-edge research is happening. This raises an important question. How do we address these hurdles, and what does the future hold for these intelligent systems? The research points to several promising solutions and a clear roadmap. embodying the forward-thinking approach of AI Coach by Anil Mathu.
Indeed. The paper outlines several emerging architectural and algorithmic solutions designed to mitigate these limitations across both AI agents and agentic AI. Let's walk through some key ones.
Okay, what are the potential fixes?
First, retrieval augmented generation, RAG. We mentioned it before. For AI agents, RAG is crucial for mitigating hallucinations and expanding static LLM knowledge by grounding outputs in real-time data from external databases. This is essential for accuracy in enterprise search and customer support. For agentic AI, RAG serves as a shared grounding mechanism across agents, ensuring a unified semantic layer and reducing inconsistencies. When applied system-wide, it helps maintain shared truth and reduces inter-agent misinformation propagation, ensuring all agents are working from the same factual base.
Giving everyone the same facts.
Exactly. Second, tool-augmented reasoning, function calling. For AI agents, this extends their ability to interact with real-world systems like APIs and scripts, transforming LLMs into interactive problem solvers that can dynamically retrieve information or execute calculations. For agentic AI, function calling supports agent-level autonomy and role differentiation, enabling fluid delegation and reducing ambiguity and task handoff, especially when integrated with validation protocols to ensure tool outputs are correctly interpreted.
Making sure agents can do things reliably.
Third, the agentic loop, reasoning, action, observation, react. For AI agents, this introduces an iterative loop for more deliberate, context-sensitive behaviors. An agent might, for example, verify retrieved data before summarizing it, significantly reducing errors. For agentic AI, react is critical for collaborative coherence, allowing agents to evaluate dependencies dynamically and adjust decisions. This requires shared memory and consistent logging to ensure the system's reflective capacity isn't fragmented across different agents.
That continuous loop of thinking and acting.
Fourth, memory architectures. Episodic, semantic, vector. For AI agents, sophisticated memory models address limitations in long-horizon planning by persisting information across tasks. Episodic memory recalls prior actions, semantic memory encodes domain knowledge, and vector memory enables efficient retrieval. For agentic AI, sophisticated memory models are crucial for distributed state management, with agents maintaining local memory while accessing shared global memory to enhance consistency and long-horizon planning across the entire collaborative system.
Giving the system a better memory.
A collective memory, yes. Fifth, multi-agent orchestration with role specialization. For single AI agents, this can simulate compartmentalized reasoning to handle task complexity by splitting an internal thought process. But for agentic AI, orchestration is central. A meta-agent distributes tasks among specialized agents, much like those in MetaGPT or ChatDev, which emulate corporate roles. This modularity enhances interpretability, scalability, and fault isolation, making complex systems easier to manage and debug.
Having a manager agent helps.
Definitely. We also need reflexive and self-critique mechanisms, agents that can evaluate their own work or even critique each other's work, like a verifier agent auditing a summarizer. This supports iterative improvement.
AI checking AI's homework.
Sort of. Then there's programmatic prompt engineering pipelines to automate prompt tuning and ensure role-consistent communication in agentic AI, reducing brittleness. And critically, incorporating causal modeling and simulation-based planning. Allowing agents to distinguish correlation from causation and simulate interventions is vital for robust planning, especially in agentic AI where actions impact others.
Moving beyond just patterns.
And finally, two crucial ones. Monitoring, auditing, and explainability pipelines essential for tracing actions and building trust, especially in multi-agent systems. And governance-aware architectures building in role, isolation, accountability, and ethical checks from the ground up.
Building responsible systems.
These solutions, collectively, pave the way for more robust, reliable, and trustworthy AI systems.
Okay, that gives us hope. Looking ahead, the paper also outlines a powerful roadmap for the evolution of AI, truly painting a picture of where these technologies are headed.
The future roadmap shows a clear trajectory for both AI agents and agentic AI. For AI agents, the focus is on enhanced modular intelligence, aiming for proactive intelligence. Agents will move beyond just responding to prompts, initiating tasks based on learned patterns or latent goals, becoming more truly autonomous.
Taking initiative.
Dynamic tool integration. They will dynamically interact with an ever wider array of external systems, from databases to complex simulation environments, to fulfill increasingly complex tasks. Causal reasoning. Moving beyond mere correlation, agents will gain the ability to infer cause-effect relationships for more robust diagnosis, planning, and prediction.
Real understanding.
Continuous learning. They will adapt their behavior across sessions and environments using sophisticated feedback loops and episodic memory, making them more adaptable over time. Trust and safety. Building user confidence through verifiable outputs, bias detection, and strong ethical guardrails will become paramount as their autonomy increases and they operate in more critical domains.
Safer and more reliable agents.
And for agentic AI as a natural extension, the emphasis is on collaborative intelligence through multi-agent coordination, contextual persistence, and robust orchestration. Future systems will exhibit massive multi-agent scaling. Specialized agents will work in parallel for complex problem-solving, mirroring, and even surpassing human team workflows and efficiency.
Huge AI teams.
Unified orchestration. Advanced meta-agents will dynamically assign roles, monitor dependencies, and mediate conflicts among subordinate agents, creating truly self-managing systems. Persistent shared memory. Sophisticated architectures will preserve semantic, episodic, and shared knowledge for agents to coordinate longitudinal tasks and maintain deep state awareness across the collective.
The collective brain.
Simulation planning. Agent collectives will test hypothetical strategies and forecast consequences within simulated environments before real-world execution, ensuring optimized and safe outcomes. Ethical governance. Robust frameworks will ensure responsible deployment, defining clear accountability, oversight, and continuous value alignment across autonomous agent networks.
Keeping them aligned with our values.
Deep domain-specific systems. Tailored solutions will emerge in fields like law, medicine, and supply chains, leveraging deep contextual specialization to far outperform generic agents in complex, real-world scenarios. This future truly positions agentic AI as a new paradigm for collective machine intelligence.
That future sounds both exciting and maybe a little daunting. So what does all this mean for you, the listener? How can you apply these insights from this deep dive and from AI Coach by Anil Nathu in your own interactions with AI, or if you're considering deploying or building AI?
Right, let's make this practical. This deep dive provides actionable guidance for individuals interacting with AI. First, distinguish your tools. When you use an AI tool, pause and ask yourself, is this a simple generative AI that's just creating text or an image based on my prompt?
Like ChatGPT or Midjourney.
Or is it an AI agent that can use external tools and act on my behalf for a specific task, like sending an email or summarizing a document?
Like some advanced email assistants.
Or is it an agentic AI system that's coordinating multiple specialized AIs to solve a complex, multifaceted problem? Understanding this helps you set realistic expectations and prevents frustration. You won't expect a generative model to browse the web autonomously if it's not designed to do so.
Know what kind of AI you're using.
Second, probe for underlying logic. When an AI gives you an answer, especially one that's critical, try to follow up with questions like, why did you come to that conclusion? Or what if this factor were different? Look for explanations, not just correlations. This helps you test its causal understanding and identify potential brittleness in its reasoning, rather than simply accepting its output at face value.
Ask why. Don't just trust blindly.
Third, observe for adaptation. Pay attention to whether your AI tools learn from your interactions. Do they seem to get better at understanding your preferences or refining their responses over time, indicating a basic reactivity and adaptation loop at play? This can give you a sense of its agentic capabilities, even if rudimentary.
See if it learns from you.
And for those of you considering deploying or building AI systems within your organizations or projects, here's some practical advice.
Okay, for the builders and deployers.
First, define your problem's complexity clearly. Before you even choose an AI solution, clearly define the nature of your problem. Is it truly a single specific task that an AI agent can handle efficiently? Or is it a complex, multifaceted goal that requires collaboration among multiple specialized AIs? As the paper warns, don't over-engineer simple applications with a full agentic AI system if a single, well-designed AI agent will suffice. Match the tool to the task.
Right, tool for the job. Don't overcomplicate.
Second, prioritize explainability and auditing, especially for agentic AI where multiple black boxes are interacting, demand or build in robust monitoring, auditing, and explainability pipelines. You absolutely need to know why a decision was made, which agent made it, and how the information flowed through the system. This is crucial for debugging, compliance, and building trust.
Make sure you can track what it's doing and why.
Third, consider role specialization for complex workflows. For complex problems, don't try to build one giant super agent. Instead, think about how to break down the task into smaller, manageable pieces and assign specialized roles to different AI agents, mirroring approaches like MetaGPT or ChatDev. This modularity can significantly improve efficiency, interpretability, and resilience.
Build a team of specialists, not one generalist.
Fourth, embrace iterative development. Recognize that agentic AI benefits immensely from agentic loops, reasoning, action, observation. Design your systems to continuously learn, self-evaluate, and self-correct based on outcomes and feedback. This iterative process is key to building more robust and adaptive autonomous systems.
Gold it to learn and improve.
And finally, integrate governance from day one. If you are deploying multi-agent systems, consider governance-aware architectures with role isolation and accountability mechanisms from the outset. This proactive approach will help you manage ethical, safety, and regulatory risks, ensuring your AI systems operate responsibly and align with human values as they become more autonomous.
Plan for ethics and safety from the beginning. That's great practical advice. We've truly taken a deep dive today into the nuanced world of AI agents and agentic AI. Moving from basic definitions to complex applications, the significant challenges they face, and the promising solutions on the horizon.
Understanding these distinctions is not just academic, it's crucial for navigating the next generation of autonomous systems and leveraging them safely and effectively in both your personal and professional life. The landscape is changing rapidly, and being able to differentiate these tools empowers you to make informed decisions.
It's a journey of continuous learning, and we hope this conversation has provided you with valuable insights and aha moments.
Think about the implications of truly autonomous systems that can not only understand your intent, but also orchestrate complex tasks across an entire network of specialized intelligences, adapting and learning as they go. It's a future that demands both excitement and careful consideration from all of us.
Absolutely. Food for thought. Thank you for joining us today. Visit the AI Coach website for more AI insights.